So our next talk is by Euan Furness. Just to start the presentation. So Euan's talk is using evolutionary simulation to improve biodiversity area models. Take it away, Euan.
Hi, everyone. Thanks for coming. I'm going to be talking here about the species-area relationship, what it is, and how we can investigate it. So the species-area relationship gets some attention in paleontology. In 1976, Stephen Jay Gould proposed using it to explain certain mass extinctions in the fossil record. And more recently, Roger Close and friends have been investigating it with respect to Mesozoic tetrapods. However, it's more broadly used in ecology circles, so for any of you who aren't familiar, the species-area relationship proposes that larger geographical areas, most commonly modelled as islands, can support more species than smaller areas. The shape of the relationship between area size and species richness is typically concave down. In other words, as areas get larger, the rate at which additional species are added decreases. There's been extensive debate about why this relationship exists. So is it the result of area per se, where larger areas reduce species extinction risks? Or is it the result of habitat heterogeneity, where larger areas could just contain more different habitats? The classical species area model is here on the left. S is species richness, A is area, and C and Z are fitted constants. C depends a lot on taxonomic group and the units involved, and Z is typically around 0.3. That's the more biologically important one. More recent models typically build on the original by adding a term to account for habitat heterogeneity, so H. Our thought was, what if we incorporate H by dividing up each area into H separate smaller areas, each with area A over H, and then summing species richness across those areas? That's where the equation on the right comes from, what I've been calling the jigsaw or area mosaic model. The basic principle is that because species richness increases at a decreasing rate as area increases, splitting an area into several smaller areas and then summing species richness across them should generally increase the species richness that we find in more heterogeneous areas, which is typically what we observe in nature. But how to test these ideas? One reason why there's still so much debate about the causes of the species-area relationship is that they're hard to test in nature, either using ecological data or fossils. So we've repurposed the rapid evolutionary simulator, RevoSim, that Mark Sutton talked about at Palace last year. RevoSim is a wonderful tool for simulating very large populations very efficiently. And as you can see on the left here, it produces a map of species distributions that essentially matches the underlying environment. Using the Palace logo as the environment, with environment type determined by color, you can see that the top of the cephalon in the logo here is covered by one genome. There's another covering the thoracic segments and a bunch occupying horizontal stripes in the blue background gradient. In our experiments, we set up environments with a defined number of colors and a defined size, and therefore a defined environmental heterogeneity measurement and a defined area. Then we filled those environments with species and let them die off over time according to first principles ecological processes. Individuals compete for resources and mates, and the smaller or less fit or plain unlucky species go extinct. That gives us a curve of species richness, i.e. diversity, against time, something like the one on the right here. A decay curve where species die off faster when there's more of them competing in the system. We can then reconstruct this curve as a rate of species loss against species richness, which, if we assume some immigration rate to the system, can give us an approximate equilibrium species richness for the system. Having done that for a bunch of different simulations, with different areas on the x-axis and different habitat heterogeneities, that's the different colors, we can see that what we get out is a series of relationships that look a lot like the classical species area relationship. That characteristic concave down curve, but with very different species richness values at different levels of habitat heterogeneity. Our new model, the jigsaw model, substantially outperforms previous models in predicting species richness from these data. And we've moved on more recently and are working with Erin Sort from Oxford to test this model on real-world data, where it's performing as well as or better than other models, even when accounting for the difference in degrees of freedom, as one must do. One thing we haven't tried yet is applying this to paleontological datasets. All the measurement problems of ecology that made us want to use simulations in the first place are amplified when you try to deal with paleo data. But it would be a very interesting thing to look at in the future and something we want to do. So keep an eye out for this, hopefully published early next year, and I hope it might be helpful for some of your own work as well. Thank you.
Brilliant. Thanks, Euan. We'll move on to the next talk. So our next talk is going to be given by Xiong. I'm going to start the slides now. Changes in seawater chemistry during the Cambrian Explosion. So take it away, Yi.
Yeah, thank you. Hi, I'm Xiong from University of Edinburgh. My topic today is about changes in seawater chemistry during the Cambrian Explosion. The Cambrian Explosion, starting at 540 million years ago, is a pivotal event for the evolution of life on the Earth. And what triggered the Cambrian Explosion is a complicated issue involving environmental transitions, ecological opportunities, and genetic development. Today, I will focus on the seawater redox conditions and molar magnesium-calcium ratio. Our study is based in thin sedimentary early marine cement from shallow reef buildings. The image is from one of our samples under the cathodoluminescence. We could see the lining crystals in luminescence near geophyte sediments. This is what we are looking for. They precipitate directly from seawater and can well preserve the original seawater chemistry. Firstly, it's about variations in carbonate mineralogy, which could be identified by petrological observations and elemental compositions. We get elemental compositions of early marine cements from electron probe microanalyses. In early Cambrian stage 2 and early Cambrian stage 4, the high manganese concentration and some microdolomite crystals in Cimbri luminescence show the appearance of high manganese calcite. But in early Cambrian stage 3, the manganese concentration is not very high, and there is no other indications of microdolomites or a crystal with flat termination, so we think they are originally low manganese calcite. We also combine the data in literature. The left diagram shows the occurrences of different mineralogies through the Cambrian. We could see two transitions from high manganese calcite aragonite to low manganese calcite, and one of the short-lived calcite appeared in the early Cambrian stage 3 in black circle, which is in accord with the findings in our studies. We also calculate the molar magnesium-calcium ratio data of early marine cements based on elemental compositions. The box whisk plots show the data in our study. We could see the data in our study dips to only 1 in early Cambrian stage 3, before rising up again to 4 in early Cambrian stage 4. Generally, our data show the variations of molar magnesium-calcium ratio shifted from aragonite C to calcite C in early Cambrian stage 3, but then back to aragonite C again in early Cambrian stage 4. However, in geochemical model from Hardy's paper and also fluid inclusion data, they only think there are only one single transition from aragonite C to calcite C during the late Ediacaran and the whole Cambrian. Based on the different data, we could see the molar magnesium-calcium ratio changes in Cambrian in a more rapid changing rate. Secondly, it's about variations in seawater redox conditions. We use LAICPMS to detect the serial anomaly profiles in different ages in early marine cement. The right diagram shows the distribution of serial anomaly data in different ages. The gray zone is the true negative serial anomaly data, which shows oxic environment. In early Cambrian stage 2, the gray dot shows the appearance of a strongly negative serial anomaly and slightly positive serial anomaly. It indicates the transition between oxic and anoxic environment. During the early Cambrian stage 3, the orange dots shows the serial anomaly data are really negative, which indicate the oxic environment. Then the data increased to less negative during the early Cambrian stage 3. The increase of serial anomaly shows the appearance of anoxic water and the removal of oxygen in shallow water. We also combine the data from Australia and South China to see the variations of serial anomaly data in the Cambrian. We could see there are two dramatic declines in serial anomaly, respectively in late Ediacaran to Fortnum and Cambrian stage 3. The decrease of serial anomaly data indicate the increase of oxygen in seawater. So we could see two periods of oxygenation in late Ediacaran to Fortnum and Cambrian Stage 3, and the gray boxes are the anoxic environment. The increase of the zero anomaly show the decrease of oxygen in seawater. That's my talk today. Thank you for your attention.
Brilliant, thanks, Yi. Okay, we're going to move straight on to the next one. And our next talk in this session is by Alycia Stigall. I'm just going to start the slides now. So Alycia's talk is The Invasion Hierarchy, Quantifying Ecological and Evolutionary Consequences of Invasions in the Fossil Record. Take it away, Alycia.
Thanks. So it's great to be here at Palaeontological. I've never been able to come before, but this is certainly easier without airfare from the US. So what I'd like to talk with you about today is a conceptual way to think about interbasinal species invasions in the fossil record. And so I published a paper on this last year. And so I know I don't have a lot of time to talk with you about it today, but I'll share the link in the chat and I hope you'll have a chance to check it out. So what I want to talk with you about is really the impacts of what happens when species move from one area to another in the fossil record. So species invasion in the context of the fossil record relates to any time you have an organism, a species that evolves in one region in which it is geographically constricted because of some barriers. Later, crosses those barriers, colonizes a new area, and then impacts the ecosystem in which it has moved into in a different way. And so that could happen at various scales from low level to high level. Let's talk through those a little bit. First, I want to remind you of how the invasion process works in the modern. So on the left of the slide, you see a diagram that's modified from Blackburn's work that talks about the modern invasive process. And you can see we go from transport to establishment, spread, and impact are different phases. You can also see through the central column that most invasions fail. So most organisms that are transported, about 90% of those just die. Only about 10% ever survive and make it into being introduced in a new region. And most of those simply form small ephemeral populations. 90% of those are temporary. As we move along, 10% of those may become established. Those may remain local, but some of those would actually spread larger. And some of those might actually go global. And we can see this process in the modern. In the modern, we're talking about very short timescales, and so you can actually see every step of it. But when we think about the fossil record, we have to deal with preservation bias. We're never going to see really small populations. We're never going to see the transport phase. But the more and more established we get, the lower down on this list, or the more kind of warm the colors become, the bigger the chances for preservation success, and also the bigger chances for impact in environmental and evolutionary space. So this is the context of the invasion hierarchy that I've worked on establishing. So let's start at the bottom. So these ephemeral impacts, you've got some organisms, they come in, they persist for just long enough to get preserved. You might see a few of them in a layer. They might be really rare fossils, they just go away. They have no evolutionary impact. They have no impact on the ecology of the local ecosystem either, because they really never integrate within it. At the isolated level, this is where we might see things like boom and bust populations. These are organisms with biostratigraphic utility that might make nice marker beds. These are throughout the fossil record, but these are also very lived in ecological time, and so therefore have very limited evolutionary and ecological impacts. Moving up the scale, we get to coordinated invasions. This is where you have multiple clades coming in, maybe unrelated organisms. The example I've got here is the Richmondian invasion from the Cincinnati region in the Ordovician. Here we've got over 80 genera that come into the basin from all sorts of different regions, multiple pathways. And when that happens, we see niche evolution, we see a decline in speciation, fundamental community restructuring. There's a lot going on. We have differential survival of generalists versus specialists. This is actually the kind of thing we also see in the modern ecosystem, where we're preferentially losing specialists. The generalists seem to do okay. Now, as we move up in the scale, we can get to even larger interchanges. We actually have full interchanges, maybe in both directions. Here we've got a picture of the Great American Biotic Interchange, when we have this fundamental change between North and South America. And as you all know from these classic stories, we've all studied in introductory class, there's a fundamental change in what happens in that ecosystem. The ecosystem and the communities, the mammalian communities and other communities of South America are permanently changed. We have differential extinction and survival of these clades, and things really become different. At the next higher level, we can have global scale changes where we actually have homogenization across global faunas. We might think of times like the late Devonian biodiversity crisis or the late Ordovician mass extinction. So large scale fundamental changes in the biotic system over time. Now, in a hierarchical system, we have emergent properties in which each level has properties not present in the layer below. And we also have downward effects. I don't have time to get into it today, but my favorite level to talk about is the interchange invasion. And I want to argue that the Great Ordovician Biodiversification Event is another beautiful example of this. This is a time that we actually see alternation between vicariance and dispersal, and we have these biotic immigration events. And so when we think about invasions in the modern, a lot of times we think about extinction and biodiversity loss, and that is absolutely a feature. But it is not a feature of every rank of the hierarchy. In some ranks of the hierarchy, we actually have an increase in speciation, and that specifically happens when we have biotic immigration events with alternation between dispersal and vicariance. And so I invite you to check out that paper. I'll drop the links in the chat. It's been really great talking with you. And I hope that perhaps you see invasions at hierarchical levels and alternating dispersal and vicariance in your systems as you're working. Thank you very much.
Brilliant. Thanks, Alycia. Great talk. So we're going to move on to our final talk of this session, which is by, let me just start the slides, by Juan Cantalpiedra. So take it away, Juan.
Okay, thank you. So my name is Juan Cantalpiedra. I study the evolution of large herbivorous mammals. And in this regard, brontotheres are very interesting because they had a very impressive role in expanding the niches of these mammalian herbivores. By looking at these plots where we represent the body mass evolution of mammalian species across the large part of the Paleogene, we see plotted figure by this orange phenogram that brontotheres helped to expand this disparity, and they become actually the first clade to really establish and dominate the merga herbivores niche, which is the herbivores above the 1,000 kilos weight. And we can see that starting from weights below 10 kilos, in just like 12, 13 million years, they multiply their mass by 300 times. So this rendered that 2/3 of brontotheres actually weighted over a ton in just a small span of time. So how this remarkable trend in body size evolution took place? So there is an obvious place to start looking at this, and is represented in the upper part of this slide, where we can see the ideas proposed by Edward Cope in his law of the unspecialized, which predicted that new lineages started with small unspecialized ancestors, and they became progressively larger and more specialized. The French paleontologist de Perret actually just isolated the aspect of the body size evolution, and highlighted the idea of this continuous increase, phyletic increase in body size in mammals due to the very various advantages of the large size and driven by natural selection. And these ideas were, of course, inspired by things like brontotheres and horses and other mammals. Of course, this came at the end to be known as the Cope rule, only making reference to the evolution of body size. In the 70s, however, inspired by the theory of punctuated equilibrium, Stephen Stanley proposed a new reinterpretation of Cope's rule. He took the idea of a small ancestor being the origin of the whole trend. That he took this idea from Cope's ideas, but he said that this ancestor would be close to a lower biomechanical limit that would make that the lower size niches would rapidly saturate. So changes in size, even though they are random, towards larger or smaller during speciation, they will tend to be more common to the larger spectrum, because this would be less saturated. So we use a few methods to test this idea. We built a topology and estimate divergence ages for our phylogeny using BEAST, and we apply phylogenetic method called fossil-BN, who estimates the phyletic trend, phenotypic rates, and ancestral sites. And these tell us that originally the first brontotheres were just around 15 kilos in weight, but they evolved really fast. So body size rates of evolution in brontotheres are up to 40% per million years, compared to sauropods, for example. They are 10 times as fast. We saw that phyletic increase is negligible. It's just 4%, and this, through several simulations we conducted, we saw that this is actually identical to actually simulations without any phyletic increase at all. So we saw that the key was that something we saw using the software Pirate, that is that smaller lineages in brontotheres just had a higher extinction risk, and this caused that species at the lower level would be less able to actually generate new species also, so that the trend would continue and expand towards the upper spectrum of body sizes. And this highlights the importance of microevolutionary process in the rapid phenotypic trends that we see sometimes in the fossil record. And yeah, that's the conclusion of our study.
Brilliant. Thanks so much. Okay, so we're going to stop that presentation, and if all the speakers could turn on their cameras and microphones, we'll go through some of the questions that have been posted in the chat. Great session, everybody. Thank you. Okay, so to kick us off, let's go with a question for Jane from Martin Smith. Martin says, a very interesting approach, Jane. How good a job do 2 dimensions do of capturing the variation in your MDS space?
So most of them do a really good job. The plot that I showed you in the presentation is just one of a couple that we've done, trying different character lists and different coding approaches, but they're all falling quite nicely underneath like the threshold for good representation. So I'm quite confident that it's doing a good job of representing the variation that we see.
Great. And Javier Ortega Hernandez asks, how do you think this would inform ecdysozoans, as decay experiments in priapulids and onychophorans suggest they are less vulnerable to stemward slippage? So
I was thinking about this one while people were talking, and I think with vertebrates, decay is a big influence on their morphology, and where you've got other groups where there isn't such a big thing, then other factors are going to come into play more. So you don't really need to have stemward slippage to use this method. You just need to know something about the different changes that the morphology might go through that you can put in. So, for example, if you knew in some weird world that it didn't decay at all, you could even just take that out and then put a different factor in. So say if distortion during preservation was more important, then that could even replace it. So it's interesting, but yeah, I don't think it's fundamentally required to use the method at all.
Great. Well, let's move on to a question for Euan, I think. Joseph Flannery Sutherland says, how easy would it be to extend the simulations to include sampling degradation, mimicking incomplete fossil occurrence data?
Okay, yeah, very possible. This is something we've discussed, actually. So RevoSim, which is the tool we've been using to create these simulated species, doesn't have the capacity to do that at the moment. But we're, or more accurately, Russell Garwood, is always making changes to this and updates to the software. And that's certainly something that we could incorporate and would help us use the RevoSim model if we're interested in the sampling distributions from paleontology rather than just modern ecology.
Great, thank you. And then we'll move on to a question for Yi. And I noticed that there's been a little bit of chat in here from Rachel and Dima too. But Duncan Murdoch asks, how rapid do you think these changes between states could have taken place?
Based on our findings, we just noticed there is minor transitions from Chalcocene to Arachnoid during the early Cambrian stage 3 and 4. But about how the changing rate, we didn't test it. I think if we want to know how rapid the molar magnesium calcium ratio changed during the Cambrian, we still need more data from different components like marine cement fluid inclusion in Canada. Yeah, that's.
Great. Yeah. So there's been a few more comments on that remark as well. So Rachel Wood has written in the chat that she thinks they might take place kind of over a 1 million year timescale, 1 to 3 million years. But Dimitri Grzdonkin has asked. He just wants to know when your work is going to be published. He said it looks really interesting.
Oh, maybe in the future. I haven't. I don't know. Yeah.
That's okay. Okay, let's move on to a question for Alycia. So it's not really a question, more of a remark. It's from Christine Janis, and Christine says, one example of ephemeral invasion that I've not seen anyone mention is bovids in North America in the late Miocene. 2 to 3 examples of Neotrigoceras teeth, and I think a horn core. So I just wonder whether you had any remarks about that.
I don't, but that's great to know about. I'll definitely add that to my list. Obviously, as an invertebrate paleontologist, I'm always looking for more vertebrate examples. So I really appreciate that. Thank you very much, Christine.
And we'll move on to a question for Juan. This is from Alessandro Chirenza. It says, any PGLS done on your data with some extrinsic factors, e.g. temperature?
No, we have not conducted PGLS, but we have played with some correlation tests with isotope curves, and we see some interesting correlation of extinction overall also over time as temperature drop over the Eocene. But we didn't have time in this short talk to talk about those correlations. But yeah, we are playing with it.
Great, thank you. And then for the final question, I'm just going to return back down the chat a little bit. I saw Rachel Murdoch has posted a question to Jane, which is, maybe you mentioned this and I didn't catch it, but I was wondering if you think there's a possibility of taking your results into account in phylogenetic analyses.
So I'm going to answer this how I'm interpreting the question, which is, I think that you can use it to inform your morphometric coding. So in the case that I showed you of the phaneroptids, we don't actually know if they're jawless vertebrates or jawed vertebrates, so we don't know where they sit. And one of the big problems that causes some of this instability is picking the wrong group to do our comparisons for homologies with. So this method kind of gives an objective way of saying, this is what my fossils have, what are they most likely to be? And then taking that and say, okay, in this case that I showed you, where they might be lamprey, so then use that to then inform looking for homologies. I'm not sure if it would work to take it directly straight from the morphology that I've used to do this, because the other thing is some of the tissue lists may be not phylogenetically relevant, but it is relevant for decay series or ontogenetic series, so you might have to tweak your character lists a little bit. But I think there's ways of making them work together and to inform on each other. Yeah.
Brilliant, thank you. So I think we'll end there, but let's say a huge thank you to all the speakers from this session. It's great to have you here. And I know some of you you've come in from a long way away, so thank you so much. Few announcements before we finish this session, number 12. So just to remind everybody again, at 12:50, we have the final of our Palace field trips for this meeting. Dr. Hilary Ketchum from the museum here in Oxford will be showing you the first discovered dinosaur, Megalosaurus. So make sure to check that out. 12:50. Links are in your link booklets. And then we're going to have a break for lunch. And so the next sessions, it's 2 parallel sessions, 13A and B, and they'll begin at 1:30. So you'll have to leave this session, but make sure to click in on the new session links in your pack. So thanks again to all the speakers, and have a great rest of the conference.